So I don't do workflows. And I think the reason that it makes sense for me to give a talk to this crowd is that task-based programming models are becoming more popular and are used very heavily now in the data analytics world and are increasingly finding application in scientific computing as well. And as you will see, there is an overlap between what the task-based programming models do and what the workflow systems try to do. And it's really just a question of granularity. Task-based systems are focused on much finer grain kinds of computations and the composition of those. And we've started in the task-based world to do things that look like workflows. Okay, and I'm not going to talk too much about that today, but I'd be happy to take questions at any point during the talk and kind of try to explain this overlap that I see a bit more. But what I'm going to focus on today is just what is Legion, what are projects like Legion trying to do. Okay, so it's a task-based programming model, and as I go through the talk, I'll say a little bit about what that means for supercomputers, these heterogeneous parallel distributed machines that you see today. And this is designed to be high performance, to be performance portable, and ultimately to be productive, to be more productive than the alternatives. Okay. And there are a lot of organizations are involved in this, including at the national labs and in industry.
Can I ask you a question?
Yeah, great.
Distributed means that you have machines, so physical separation.
Yeah, so distributed means in this case that you have multi-node supercomputers, right? So they're all considered one machine under one job scheduler. So not geographically distributed, but physically distributed. Yeah.
But can they also be geographically distributed?
We actually have plans.
The same,
yeah. So currently no, but there's no barrier, and actually it's in our roadmap to do that. And there's nothing in the model that says it couldn't be that way. We just haven't done the engineering to make that happen.
So is there any distinction between what you are going to tell us compared to regular leadership class computers like Summit, Frontier?
Now you should be thinking about machines like Frontier, exactly when I talk about these kinds of machines. Okay, and let me tell you about I'm going to kind of to frame the talk. I'm going to talk about a few different applications from different domains. All right, and so first one is a combustion chemistry application that's been written in Legion. It's designed to simulate any chemical reaction you might like. So there could be different numbers of species as part of the input, and like all other kind of combustion chemistry simulations, it has two parts where there's some physics, and then there's also the chemistry, which is strictly local and very complicated in terms of which reactions are present in any given chemical mechanism. So here's some old results, weak scaling this. In Legion versus versus MPI Fortran. Okay, and you can see, the Legion line is above the Fortran line, but the most interesting thing is that at small scales, it was a 3x improvement, all right? But at large scales, the improvement was actually larger. Okay, so that it actually scaled better, and this is because I'll explain a little bit more about why. But this is basically because the task-based systems are inherently asynchronous, and they asynchronous by default, and that just deals better with these large machines where the latencies are unpredictable. So as you scale up and you can't really tell exactly how long say communications are going to take, having a system that tolerates asynchrony better does lead to performance benefits. Okay, so there's some other things that led to the improvement. I'll talk about these as we go along. One that we think is a really big deal is sequential semantics. So that when you write in these systems, you write like you're writing in a normal sequential program. And it's up to the system to discover and extract the parallelism. And this just makes debugging way easier, all right? And then another thing I'm going to emphasize is late binding of performance decisions. So I think one of the weaknesses of the way we program these machines today in systems like MPI is that you have to bake in a lot of your performance decisions before you ever run the code. Essentially, when you write the code, you're making a bunch of performance critical decisions that you may discover later on you wish you had done it differently, and generally result in massive rewrites if you have to undo them. Okay, and the way these systems are designed, those decisions are postponed to a much later stage, and it's much lighter weight to change them. Okay, which makes it easier to performance tune when you get to that stage. All right, so sequential semantics. So here's a skeleton of what the S3D code looks like. You'll have your simulation volume. You will actually explicitly partition the data in a couple of different ways. So you'll be talking about your simulation, and you will then define partitions of it. And then you'll call these things called tasks, which are just distinguished functions that can be run in parallel by the system over and over again in one of these loops, alternating chemistry and physics until you're done. Okay, and so your tasks defined somewhere else. Okay. So there are no race conditions in this model. So when you have a bug, you can use kind of conventional debugging techniques to find it. If you want to relax the sequential semantics, you can. There's obviously situations like parallel reductions when you would like things not to follow strictly sequential rules, but this is something that's under your control, and you can decide how much you want to leave the kind of sequential semantics world when you're writing these codes. Just to give you, I showed you some pseudocode. Here's just what some actual code looks like. This is taken straight out of the current implementation of S3D. And you can see the same structure I talked about before, where you have a loop and you're launching a task over a whole bunch of ranks of your data. All right. This is actually written in a programming language called Regent, which is just a programming language for the Legion C++ API. So it's a little bit higher level than the C++ API and hides some details. All right. So so when you have these asynchronous models, asynchronous tasking models, it's easy once after the program is written to change how you partition the data. Okay, so you can go back and change your mind about how you broke the data up. It's easy to move the tasks around to decide, like, I want to run this task on the CPU or I want to run that task on the GPU, and to change where the data lives. So you could decide, for example, that your frame buffer memory on the GPUs is oversubscribed, and that's the cause of your performance problems, and so you want to move some tasks back to the CPU and move the data, say to zero copy memory or something like that. All right. So, and so we do this in a process we call mapping. So you can, decide. You write a separate mapping for your programs. The program I showed you didn't say where the tasks would run, for example, or where the data would be placed. And so you can separately specify where these things are going to happen. So this is a mapping file. It says things like, by default, all tasks will run on the GPU. So you say the way you read that is, every task, so that's the wildcard star, it'll run on the GPU if it has a GPU version. Otherwise, it'll run on the CPU. Then there's certain tasks where we override that and say that we're going to definitely put these on the CPU because we don't want them cluttering up the GPUs. And then regions, these are the collection arguments. So these, like, you can think of them as multi-dimensional arrays. And these are going to be, so all GPU tasks will have their data placed in the frame buffer memory, and all the CPU tasks will have their data placed in the system memory. All right, and then you can also say things like what layout you want to use for each region, and the in this case structive arrays and Fortran order on the dimensions. All right, so I think the secret sauce really for us, and I think we've seen this over and over again in different applications, is that the ability to easily change these performance relevant decisions after the program is running has been the key. All right, and we often will play with the mapping and the partitioning over and over again, once we have the ability to get feedback, once we actually have the program running, to find the best strategy. Okay. And it's not that you couldn't do this in something like MPI. It's just that it's a whole lot easier to do it and more productive. All right, and so I think this is where the productivity improvement comes in. I mean, it's like once you have your program running, your ability to tune it for a particular machine and your ability to port it to another machine and retune it there is much higher, just because you have these hinges where decisions aren't fixed by the way you wrote the code initially. All right. Now this actually extends, in ways that we didn't anticipate. So people have found application for this capability that wasn't obvious at first. So here's S3D with a 48 cubed per rank problem simulating heptane, okay, which is a relatively small chemical mechanism. And here the best mapping that we could find used a lot of CPUs to run some tasks, as well as, in this case, this particular machine only had a single GPU on it. But then for a bigger problem size for heptane, like we were going to put 96 cubed points on each node, it turned out that a different mapping was appropriate, just because the balance between the chemistry and the physics changed on each rank. And so what this means is that you would potentially do this tuning even for every input. When you change the chemical mechanism, or you change the how you're packing, what problem size you want to run per node, this changes the balance of things, and the optimal strategy will be different. And the ability, and actually making it productive for people to find those, to make it worthwhile, the fact that it was easy to make these changes made it worthwhile for people to actually tune for different inputs and see significant performance improvements. All right. So, so the impact, this is one of the applications we've had for the longest and has been used the most. And so the impact of this ability, to tune things easily and to port it has just resulted in many more implementations and ports of Legion S3D than the old MPI S3D. So since the Legion S3D was written a number of years ago, it's been ported to basically every supercomputer that has existed since then, every leadership class machine anyway. And there are many, many more variations of Legion S3D, because if you add a new task or something else that changes things, then it's a relatively simple matter to go back and retune if that has significantly affected how your computation behaves. And so an example here is a simulation of PRF, which is a much, much bigger chemical mechanism. This resulted in just massive changes in how you wanted to map the program, but that was a relatively straightforward thing to do with Legion. So just to summarize this piece of the talk, if I was to do a head-to-head comparison between writing in Legion and MPI, in Legion you have sequential semantics by default, and in MPI you're doing explicit parallel programming. So you have deadlocks and races that you potentially have to deal with. And typically, if you want more performance, that means you have to do fancier concurrent programming, and you expose yourself, to potentially having those kinds of problems. All right. Legion is asynchronous by default, meaning that the tasks will run when they're ready to run. The system is responsible for the data movement. It will do the communications whenever it can, so the communication and the computation can overlap by default. The system figures out where the dependencies are between the tasks. Okay, this is the place where it connects to the workflow systems. It is figuring out, your tasks are your units of computation. It's figuring out which tasks have to run in which order, and what data has to be moved where. MPI, there are definitely lots of asynchronous things in API, but the thing that people use the most is the age-old synchronous mechanisms. Legion has what we call a strong data model, meaning it knows what data you're using, it knows how it's partitioned, it understands the relationships among those partitions of the data, and you have late binding of performance decisions. Now, it isn't all, butter and honey or milk and honey. Milk and honey is the right one. Yeah. And so, what's the downside? What's the price you pay for that? You have higher runtime overhead. You have a system that's giving you more services, and so there's a cost to that. You are spending some resources on the runtime system itself and on the analysis that it has to do to provide these services. Whereas, something like MPI, you have absolutely bare bones, minimal overhead from the library. It's not really, it's not really doing, and it doesn't do as much for you. Okay, so that is the trade-off. All right. All right, so now I thought I would just emphasize this aspect of the strong data model. And I'm going to talk about this because later in the week, Seshu, who is sitting here, is going to talk about some more recent work built on top of Legion that and I don't want to steal his thunder. So he's going to talk about people using NumPy libraries in a parallel and distributed fashion on top of Legion. So I'm going to focus on other things. All right, and I thought this is one of the more interesting things from a technical point of view, and perhaps of interest to this audience. So partitioning data is a really distinctive feature of distributed computing. Okay, so whenever you have a physically distributed memory and you want to take advantage of that, you have to decide how to divide up your memory. You have to decide how to divide up your data, excuse me. And so the question always comes up in any kind of distributed programming: how should you partition your data? So let's take an example of an irregular graph computation. This is taken from this particular example is an electric circuit. So the edges here are wires, and the nodes are where the wires connect. And let's say we want to partition this irregular graph into 3 pieces. All right. So how would we express this in Legion? So we would have what's called a collection or a region of nodes, and I'm only going to focus on partitioning the nodes here. We'll ignore the edges. So just going to focus on how the nodes get split up into the 3 groups here. And so it starts out, in the system nodes, you declare that you have a set of nodes. And then the first thing you're going to do is, in idiomatic Legions, you're going to partition this into what we call the private nodes and the shared nodes. All right, so this might not be what you expected, but essentially the private nodes are the nodes that are in the interior of the pieces and don't have an edge to another piece. And then the red ones here are the shared nodes. They're the ones on the boundary of a piece and have at least one neighbor who's in a different piece. So the shared nodes are where communication will happen with other pieces. And the private nodes can be buried somewhere deep in the memory hierarchy because they're not going to need to talk to anybody else outside their own piece. Okay, so that's the intuition for why we want to break things up that way. All right. And then, once we have the private and the shared nodes, well, we can then talk about the 3 pieces. So there'll be 3 separate sub-regions of private nodes. So here I'm just showing the private nodes for the first piece, okay? But there's 2 other subsets of the private nodes. So we'll partition the private nodes themselves into 3 subsets. And we'll partition the shared nodes into 3 subsets. And again, I'm just showing the subset for the first piece here. But this isn't the whole story. And the most interesting piece is that there's actually one more subset that we need to name to be able to express the computations we want to do. And that is the ghost subset. So every piece needs to exchange information with the nodes on across its boundary and other pieces. And so there's another set of nodes that's relevant to this first piece, which is the ghost nodes. These are the nodes that are in another piece but connected to a shared node in piece 1. All right, and every other piece has its own set of ghost nodes. Okay. And the interesting part of this is that the ghost nodes of one piece are the shared nodes of a different piece. All right, so we can see here that really the ghost nodes are just a different partition of the shared nodes. And so these are 2 different views onto the same data. Okay, so if you're a database person, you would call these views. But these are just 2 different ways of partitioning the shared nodes into subsets that are relevant for different parts of the computation. Okay? And so this is how you express your data in Legion. You would actually name all of these sets. And this is how Legion will track and infer communication. So when you say update the shared nodes, all right, of a piece, and then later on read through the ghost nodes, Legion will realize, these ghost nodes might actually overlap with those shared nodes you updated, and I have to go and find those pieces, do a gather to get the most recent data for that task that's using the ghost nodes. All right. So this is the data model in Legion. Now here's an example, just showing a task. So this is one that distributes the charge, and it takes in the 3 regions for a piece, the private, shared, and ghost nodes. And then it also takes in a region of the wires, which we didn't talk about. But and then this piece down here declares how the task is going to use those regions. So it's going to read from the wires, some of the fields of the wires region, and it's going to perform reductions into the private nodes, the shared nodes, and the ghost nodes, but just to the charge field of each of those three regions. So Legion uses this information to both figure out what data is required for the task and also to infer dependencies between tasks when it's executing the program. All right, so again, tasks are the unit of parallel execution. Regions are these n-dimensional tables. You can think of them as arrays or tensors. They have type columns, which are fields. And then privileges declare how a task is going to use its region arguments. All right. And just interestingly, this particular task uses both views of the shared nodes, both the shared piece and the ghost nodes for that piece. All right. Now, I'll just make a point here, and this is actually one place where we cross over a little bit into workflows. All right, and I think of workflows potentially as just task-based systems at a much coarser granularity, where you have big blocks of things with dependencies between them. If you really want to compose software together, parallel software together, in a way that is scalable in the software engineering sense, you're going to need multiple partitions of your data, and you're going to need to understand that. All right, and why is that? So, well, if I have two libraries that are written independently, okay, there's no reason to assume they're going to use the same partitioning strategy for the data. I mean, organization A writes a library, organization B writes a library. I would like to use them together in my system. All right, so today, the way you compose those two things is because you can't assume that they actually have the same view of the data, is that you have to basically stop the world. You run one library and everything stops when it's done. And then you completely shuffle the data into the view required for the second library, and you restart the world and run that. With these task-based systems, you don't have to do that. I mean, because they're just all tasks, and the analysis is done at the granularity of the individual task, and it will figure out what data is needed. So you can potentially overlap the interaction between the libraries and co-schedule them and do optimizations that you just can't do today, and make much more efficient use of your resources. Okay. All right. Okay. So that's my pitch. All right. And an example that we have played with, and it's a pretty common example, is you have a simulation, you have a solver, and you have a visualization library, right? And you'd like to put them all together in a data analysis pipeline. And they have different needs. They look at different pieces of the data, but you'd like not to have these huge boundaries between them where basically everything has to stop, and then you have to move a lot of data and restart. All right. So to support this data model and this view of partitioning the data, Legion has a very rich subsystem of partitioning primitives. And I'm going to get down into some little more technical detail here before I start to come back up for air towards the end of the talk. Just to tell you about some of the cool things in the partitioning model of Legion. Okay, and it's basically a little sublanguage for partitioning data that is compositional, and by combining the primitives, you can express very sophisticated partitioning strategies. So one of these is partitioning by field. So this thing I told you before, where we take the nodes of this graph and color them either blue or red, how did that actually happen? So the way you would do this in Legion is you would have an extra field in your nodes region, and you would use some other tool like Metis or ParMetis to go through and decide how you're going to partition this graph, and to just say, okay, like I want this node to be a shared node, that node to be a private node. So you'd have a bit field here that would label each node, and you would do this as a separate computation, which itself could be parallelized and distributed. But then what you would tell the system is, I want to partition this node using the S or P. I want to partition the nodes of region using the S or P field. Okay, and so everything with the same value in this field will go in one subregion, and so you'll wind up with two subregions here, the shared and the private nodes. All right, so you can compute an arbitrary partition of the data, and then store it in a field, and then use partition by field to get the data, to tell the system, to inform the system of what that partitioning should be. So partitioning by field is what we call an independent partition. It's a partition that doesn't depend on other partitions. Another example would be something simple like just split a region into equal parts or close to equal parts. But the interesting thing, I think, about the partitioning sublanguage is that we have dependent partitioning operations where you can compute new partitions from existing ones. All right. So here's two very useful operators, it turns out, that allow you to co-partition multiple collections. So the basic idea here is to treat a pointer field from one region to another as a function, and to take images and pre-images of that function to define partitions. So let's say region 1 has already been partitioned, okay, and it has into these three subregions, red, green, and blue, and it has a pointer field into another region. All right. Then intuitively, what partition by image says is just copy the color along the edge, and then partition the destination region, according to the source of each edge. All right. So, for example, everything that had a red, everything that was in the red subregion, region 1, everything that it points to would be in the red subregion in region 2. Okay, and similarly for the blue and the green. All right, and one thing about image partitions is that pointers, this might not be a injective function. Okay, it might have multiple pointers to the same data, in which case those elements are just in both subregions. Nobody said that, we call it a partition, but it doesn't have to be a mathematical partition. So, you can do just naming subsets. So this element would be in both the green and the blue subregion in region 2, for example. All right. Okay. And then partition by preimage is just the inverse operation. So you start with a partition of a region. You have some pointer fields into that from a different region, and now you follow the arrows backwards, and the color spreads along those arrows, and you partition the source region using the colors of the destination region. All right, and this one, because every pointer has a unique source, you're guaranteed that if the original partition was disjoint, then the preimage will also be a disjoint partition. Okay. All right, so this is like extremely useful for some very common and important operations that we would like to do. In particular, I'll talk a little bit about how we do sparse matrix representations. So here are a couple of different ways of partitioning a sparse matrix. Here we've partitioned it by row. Okay, so all the elements in a row are in the same subregion, in the same group. And here we've partitioned the sparse matrix so that each subregion has a balanced number of elements. In this case, each one has 2 elements in it. All right. Okay, so how can we express those two partitioning operations? Let me tell you about one more idea, and then I'll be able to show you visually very simply what we do. So I'm going to represent these sparse matrices using coordinate trees. So the first line here is just the row. Okay, and then the second line, and then for each row, we have children here, which represent the coordinates within the row that have non-zero elements. So in this case, 0, 1, and 3 in row 0. Elements 1 and 3 in row 1, and so on. Okay, and then the last line is just the elements themselves laid out in a single vector. Right? So this uniquely names the position of each element. And this is just a standard sparse matrix representation dressed up in a slightly different way. I mean, very frequently you'll have these 3 vectors in a sparse matrix representation, and we'll store them in 3 different regions. So the row identities will be stored in region 1. The coordinates with the columns will be stored in a region 2, and then the values will be stored in a 3rd region. Okay. All right, so pretty standard setup. But now, to do the partitioning, if I want to do the row-wise partition that I had up before, well, that is just taking images, right? So I'll start with a partition of the rows. Every row is in its own subregion, and then I'll follow arrows, pointers down, and spread that partition to color all the elements in each row, and then the values according to according to the original image partition. So I'll partition the rows, and then I'll do an image partition of the columns and then of the values. All right. Okay. So 2 image partitions. If I want to get a balanced partition, I'll first partition the columns vector into equal pieces. All right. And then I'll do a pre-image of the rows and an image of the values to get the right associations. Okay. All right. And again, since you will wind up with some values here in more than one region, since in this case, the columns span more than one partition. All right, for that row. All right. Okay. All right, and again, I think one of the advantages of this is, first of all, besides being very compact and also telling the system exactly what data is going on, so then the system can manage that data, it's also easy to change these things. I mean, it's like if you have a certain partitioning strategy and you want to try a different one, this is just a couple of lines of code now, rather than a lot of more complicated manipulation of data structures to express these different choices. All right. How am I doing on time? Okay. So I already said all this. So let me go on to talking about task-based libraries. So again, I think here's a touch point potentially with workflows. So the internal representation of a tasking program inside of a system like Legion is as a task graph. You have tasks, and the system figures out what other tasks it depends on and what other operations have to be done, like data movement. And in the end, there's just a giant graph of operations that have to be performed with dependencies between them. Okay, and this is naturally compositional across libraries. If I have a library, that can be represented as a graph of tasks, and I have another library that can be represented as a graph of tasks, putting them together is a graph of tasks, right? And so this is something that naturally composes in a way that taking one MPI program and another MPI program and putting them together does not. Okay. And the late binding of decisions makes those interfaces also flexible. So the libraries can now be parameterized in ways that weren't possible before. Like it can be parameterized in how the data is partitioned. The library it doesn't have to have a fixed partitioning strategy. It can query, like, how did the client want the data to be partitioned? Where did the client want the data to be placed? Okay, as opposed to saying the data has to be in a particular spot, okay, or partitioned in a particular way. All right. And finally, the other thing we can do, which I haven't stressed yet, but it seems a natural extension, is that we can automate the search for those best strategies. So once you have a way of kind of expressing a family of strategies, like some kind of notation for like how things are assigned, then that defines a search space, and you can build higher level tools that will try or in some way search over those different strategies and automate the tuning of the program. Okay, so just to make this pictorially, so I have 2 task-based libraries that expand, and a library here might just be a single task, but because tasks can have subtasks, I mean this task might expand into some big graph. And then when I put them together, the system, if I say I want to run task 1 and then task 2, the system will figure out where the data dependencies are and add appropriate edges, and I'll get a new composed task graph. All right. So let me tell you about one application of this. They're kind of putting everything together. I'll talk about the work we've been doing recently in tensor algebra. So we have a library for dense tensor algebra that we did first, and then built on top of that another library for sparse tensor algebra. And the basic idea here is that you write down your tensor algebra expression. It doesn't look quite this nice. It's in some ASCII notation, but you basically write down in a little DSL what tensor algebra expression you want. And then we have a little compiler that will generate Legion code to implement that particular tensor algebra expression as best as possible. Okay? All right. And so the classic tensor algebra operation everybody cares about is distributed matrix multiply. So here are all the classic distributed matrix multiply algorithms, right? And here they are, in a prettied up version of Distal's DSL. We have to describe the target machine because these machines are, the algorithms themselves actually organize the machine sometimes in 3 dimensions or 2 dimensions or whatever. We have to talk about the data distribution, so we have a little language, for describing how the matrix should be chopped up or the tensor should be chopped up. And then we have a bunch of, basically a script for describing how the tasks should work on that data, okay? And that is the full script. I mean, this is actually the full description of each of these algorithms, all right? Okay. And so then comparing, our kind of generated code with, standard implementation, standard libraries. So, here's Cosma. This is on CPUs here. So this is Cosma, which is currently the world-leading handwritten implementation of distributed matrix multiply. Here is Distal's Cannon's algorithm automatically generated. Okay, so, and then just for comparison, here's Scalapack, down here, all right? And then here's some GPU numbers. This is Cosma, again, on the GPU. This is Cannon's algorithm from Distal, all right? And this sawtooth behavior here is actually expected with Cannon's algorithm for different, machine sizes. Okay, so that's not a bug. That's just kind of the way the algorithm behaves, and that's actually what Cosma fixes. Is it makes it a little more uniform in its behavior across different numbers of nodes. But anyway, we're within a small constant factor of Cosma, and this was automatically generated code. But the main point here is that this works for any tensor algebra expression, not just the ones that people have beat on for 30 years. So you can write down any tensor algebra expression, and it will do a good job of producing code for that. So here are some less commonly used tensor algebra expressions, and comparing to another general system, and you can see there's just a huge gap generally in performance. Here. All right. Okay, and then also same story on GPUs. And as I said before, we did this also for sparse tensor algebra. So for sparse tensor algebra, what you see here is a range of performance. So there are error bars around these because the performance differs with the exact sparsity pattern of the test matrices. Okay, so you don't get just one performance number. We tried these across a range of things. But you can see that the blue band is sparse distal, and then PETC and Trilinos generally are a little lower. Okay, and then this is on SPMV, which is one everybody does well. So the numbers are all kind of up here at the top. But then when you get into the ones that are more custom that you don't see every day, sparse distal does a better job of generating code for those. All right. Okay, so I'm going to wrap up with one last library that we've done. So this is called FlexFlow. It's basically a drop-in replacement in Legion for something like PyTorch or TensorFlow. Actually, for PyTorch and TensorFlow. And the basic idea behind this was that we could exploit Legion's data partitioning to partition tensors in ways that PyTorch and TensorFlow don't consider. So they have a few parallelization strategies and for training. But there's lots and lots of other ways you could chop up the data that potentially, depending on what specific operations you're doing, might result in more efficient schedules. Okay. And the second idea is what I mentioned before, and this is the example I wanted to show you for this reason. This is a place where we've actually gone, that next step and automated the search process for in the performance tuning. So instead of writing the partitioning strategy by hand, FlexFlow searches over possible partitioning strategies. Okay, and it does this for every layer of the deep network. So it'll pick a different partitioning strategy potentially for each network layer. And the bottom line, how am I doing on time? Is I'll show an example here. So, here's an example. This is a kind of standard way of partitioning data that you would get out of the box with something like TensorFlow or PyTorch, representing data parallelism. Okay, and I'm showing I'm showing partitioning in only 2 dimensions here. FlexFlow handles more. The sample dimension is basically the data dimension. Okay, so that would be if you partition in the sample dimension, you're getting data parallelism. And then the parameter dimension just has to do with how you partition the parameters of the network and where you distribute, and then you're ultimately going to distribute them. So standard TensorFlow out of the box or PyTorch out of the box is going to give you data parallelism for every element of the network. I forget which network this is. This is some standard network. Okay. Maybe the name will come back to me in a minute. But this is like one of the most common. I think this is Insight, actually. I think that's what this is. But anyway, this is on 4 GPUs, so every level of the network is partitioned. Every operator in the network uses 4 GPUs and partitions its input, into 4 equal pieces for processing. And here's the strategy FlexFlow comes up with for this. And the only thing that's interesting here is you can see it does use data parallelism, especially in the early stages where there's a lot of data. But as the amount of data is reduced, you can see that it starts to, prefer parameter parallelism in some places. And in some places, it does partitioning in both. For some elements of the network, it turns out it's worthwhile to partition in both dimensions. Okay. So that search is automated. So it picks some partitioning strategy. Here are the most recent results on a large model. So this is BERT large, and this is comparing with Megatron. So if you're not familiar with Megatron, it is a handwritten, parallelized version of this model. Okay, so hundreds of engineers, literally thousands of hours of work. All right, and so the FlexFlow is completely automated and gets within a few percent of that. And then some other, and then this is the old version of FlexFlow. So Unity is the new version of FlexFlow. This is the old version of FlexFlow here in orange. And DeepSpeed is another commercial effort that I think from Microsoft, I think. Okay. All right, and this story, pretty much plays out across lots of other networks as well. All right, where the automated search for the partitioning strategy pays off, and it makes sense. I mean, like if there's something you're not doing, and somebody else comes along and is doing it, namely, exploring ways of partitioning the data, and given that data movement is so important, you're probably going to find some wins, and that's what happens with FlexFlow.
Is there any specific reason why for ResNet it's no difference? I'm just curious.
ResNet, because ResNet is basically is close to optimal already with data parallelism. It's a simple enough one that basically there's not much to get. So like so sometimes data parallelism is what you want to do. Yeah. All right, so I think what's happening now is that people are writing libraries on top of Legion and starting to develop this ecosystem of task-based systems. And we're getting to the point where people are going to start putting these together into bigger things, and we'll have workflows. Okay. So the one that Seshu is going to talk about is QNumeric, which is an effort from NVIDIA. This is an open source drop-in replacement for NumPy. So you write a NumPy program, and then it does all the magic to partition the data and distribute it and maps it down to Legion. Okay, but your NumPy program will run parallel and distributed, just as a raw NumPy program. Legion solvers is close to being done, but I've said this for a number of months now, but we really are pretty close. These are sparse iterative distributed solvers, another library. And then distributed sparse SciPy is another Python library that we're working on accelerating using Legion. All right. So to summarize, task-based programming systems provide a sequential model with implicit parallelism. I think that this idea that we have exploited of late binding of performance decisions or finding ways to defer performance decisions so that you can make them late has really improved productivity and been the key to achieving the best performance. I mean, so we don't have to do lots of work when we want to change our minds about where tasks run and where data is placed and how data is partitioned. Okay. And then this strong data model is also very important, because without that we couldn't teach the system or tell the system how we wanted to partition the data and have it manage all the data movement and allocation of space and shuffling for different layouts and things like that. All right. And with that, thank you for your attention, for tolerating me as an outsider to your community, and I'd be happy to take questions.